Hi, my name is Jin Choi. I'm going to do three things in this video. I'm going to show you how to create an LSTM model to predict stock prices. I'll also discuss why LSTMs might theoretically work for this task. And finally, I'll talk about whether we can actually make money trading with this model. Let me start with some sample code. I created a GitHub repo that contains a fully working LSTM model, which you can access using the link in the description of this video. I'm only going to cover the important sections of this code and skip the boilerplate. But if you have any questions on some of the code I didn't cover, feel free to ask me in the comments. Let's begin at main.py file, which is where the code execution begins. The first thing we do is download price histories from Yahoo. In this project, I've chosen to use the entire price history of SPY, which is an ETF that tracks the S&P 500 index. Financial pros often use this index to represent the entire US stock market. But the model we're going to create doesn't have to try to predict SPY in particular. You can choose to model individual stock prices instead of swapping out the ticker. To train on Apple's history, for example, just replace SPY with AAPL. You can also use prices from multiple stocks to train the model, but I'm not going to do that here to keep the code simple. Let me know in the comments if you would like to see a version of the code that uses multiple stocks. Notice that I'm only taking the closing price of each day. These are the prices at the end of each trading day, and it's the one that investors are usually most interested in. But you could devise another model that uses other price data, such as lowest and highest prices of each day. I'm not going to do that here to keep things simple. But again, if you would like to see an example, please leave a comment. I also take this opportunity to remove any missing data using the drop NA method. I don't expect there to be any missing data, but why take the chance? Next, you see that I took the percentage changes in prices. Doing this removes the level of prices from the data, and I'll explain why this is important later on. Let's now pre-process this data to reshape it into a form that the model can make use of. But what form should the data take? That decision flows from how LSTMs work, so let's review that. LSTMs process data sequentially. It looks at each data point like the scenes of a story and tries to remember the important bits of the plot. This is meant to mimic how we humans process stories. When we look at a comic strip, for instance, our brain subconsciously remembers who the characters are and how they're feeling. One reason LSTMs might be able to predict stock prices is because it may be able to learn how traders feel when they experience a sequence of returns. To facilitate this learning, we need to reshape our data into episodes. In this project, I've set each episode to be a sequence of 10 data points. We don't have to set the sequence length to 10. It can be any number you choose, like 5, 23, or you can even let it vary for each episode. Longer sequences can give LSTMs more context of the stories they're evaluating, but it also consumes more memory and processing time. I just happen to choose 10 because we get each data point for each business day, and that means each sequence spans around 2 weeks. And I think 2 weeks is long enough to form feelings inside traders. But you can experiment with other lengths if you'd like. When the sequence length is 10, one sequence, for example, may go from August 7th to August 18th. The next sequence may go from August 8th to the 21st. These sequences overlap, but that's not a problem. The process inputs method handles the logic of creating these sequences. I won't go through the logic of this method line by line, but if you have any questions, feel free to ask me in the comments. When you run the method, the resulting data looks like this. T-9 contains SPY returns 9 trading days before the reference date, which for the first row means 9 days before February 12th, 1993. T-0 is a return on the reference day, so February 12th. Now I want to take a moment to talk about why we chose to use percent changes for inputs. If we didn't take percentage changes, the data will look like this. As you can see, each row would be at a different level. In the early 90s, the level would be around 25, whereas in the early 2000s, the level would be near 60. The latest data's level would be around 450. If we use these data points, we would force the model to take notice of these level values. The model would treat each sequence in the 90s differently from the sequences in the 2000s, and so on. But do we want that? Probably not. Traders generally don't care what SPYs or any stock's level is at. All they care about is whether it went up or down. We also want the model to learn principles that apply across all eras, but these different levels would confuse the model. So we remove the level info and focus solely on the magnitudes of ups and downs. That's all we need to do for the inputs, so let's now organize the targets, which are the data points that we're trying to predict. Targets are like the correct answers in an exam, and LSTMs are like the students taking the exam. LSTMs, like all machine learning models, learn by making guesses and seeing how far off their guesses were from the correct answers. For predicting stock prices, you might be tempted to set the target as a data point right after the reference date. So for the second row in the data where the reference date is February 16th, you might instinctively choose the target as February 17th, but that would be a mistake. Think about how you'd use LSTMs to trade after you've trained it. If today is February 16th, you'd wait until the stock market is closed on the 16th to gather the data. And if the model tells you the markets will go up, you'll buy the stock. But when would you buy it? You would buy it when the market opens again on the 17th. But the model was trained to predict how prices would move from 16th to the 17th. So if you wanted to utilize the predictions properly, you would have had to buy on the 16th. In other words, you'd be too late to buy by the time you buy. This is a common mistake that even a lot of PhDs make. It's one reason why machine learning still hasn't caught on in finance. A lot of PhDs create these models that look great because they set the wrong target, and they only realize their mistake after they try to trade. I get around this problem by trying to predict price moves 2 days in advance. So using data up until the 16th, I try to predict what happens from the 17th to the 18th. It's harder to predict 2 days in advance, but at least the model will be usable. The process targets method sets up the target data. After running the method, the data looks like this. The index shows the reference date, and the data is from 2 days after the reference date. The next 2 lines of code discards rows where we don't have both inputs and targets. This can happen if, for instance, we didn't have input data 9 days before the reference date, so we couldn't construct a full input. In the next 3 lines, I isolate the training data set. In this code, I've decided to use all data before 2020 as the training data. I'm going to train the model using only the training data set, and then I'm going to evaluate the model using only the test data set, which is the data starting in 2020. This separation is crucial. If you don't do this and evaluate your model using the same data you trained with, you're going to think the model performs much better than it actually does. This is an essential concept, yet I sometimes even see professionals making this mistake. And this is one reason why machine learning strategies haven't been popular in the investment world. Many of these so-called machine learning experts devise strategies that look amazing on paper because they fail to separate training and test data sets. And when they release a product based on the strategy, the product doesn't perform nearly as well as expected, and that gets investors to think that machine learning sucks. Let me stop my rant and get back to the code. The data prep is done, so now we get to the fun part. We get to look at the model. The model definition is in model.py. As you can see, I used the PyTorch library to construct this model. The LSTM stocks module class stitches lower level components together so that calling the forward method turns inputs into predictions. The first lower level component is the LSTM module itself. Let's talk about the arguments of this module's constructor. The first argument, hard-coded as 1, defines the input feature size. In our case, we're only using the closing price, so we only have one feature. If you want to use multiple features, say by also using the opening price, you'd adjust this number. The second argument shows a number of hidden nodes to use. You can think of this as a number of memory banks inside LSTMs. Using more hidden nodes allows the model to track more facets of the data, but more hidden nodes also make the model more prone to overfitting, which is a tendency of our model to memorize specific outcomes rather than to learn more universal principles. You normally try to strike a balance between these two forces. I've set the number of hidden nodes to 2 here, but feel free to experiment with other numbers. The next argument determines the number of layers to use. You can layer LSTMs like you layer a cake. You just stack one layer on top of another, which would have the hidden nodes of the lower layer be inputs for the higher layer. Using more layers is a bit like using hidden nodes in that it increases the analytical capacity of LSTMs, but it also makes them prone to overfitting. I've chosen to use a single layer, but you can experiment with more. The bias argument is difficult to explain, but setting it to true also increases the analytic capability of LSTMs just in a different way. But again, setting it to true slightly increases risks of overfitting. This is a common theme among all machine learning models. You can devise a million different ways to increase its ability to learn, but each one of those ways increases the risk of overfitting, so you have to balance that. This is especially true with financial machine learning because the data is often very noisy. The last batch first argument is more for convenience. By setting it to true, we allow the first dimension of the data to indicate the different sequences. Without this flag, we'd have to rearrange the data so the sequences line up along the second dimension. The linear component is there to combine the outputs of the LSTM. The output of LSTMs have the same size as a number of hidden nodes, and we need to use those outputs to produce a single prediction for each sequence. And the linear component, without the bias term, allows us to take the weighted average of the outputs. If there's only one hidden node though, taking the weighted average is not necessary, so we don't even create the component. As a side note, we don't have to use linear component to combine LSTM's outputs. You can use more complex components if you'd like, as long as the components produce single outputs. But then again, more complex components would increase the risks of overfitting. Taking the weighted average is one of the simplest methods, and that's why I've chosen to use linear. The forward method of the LSTM stocks module class handles the actual job of processing inputs into outputs. Most of the code is self-explanatory, but let me note one thing. LSTMs produce 2 outputs we can potentially use. Cell contains contents of LSTM's memory banks, while hidden is some combination of inputs and cell states. You can experiment with using either, but it's more typical to use hidden, so I use it here. Let's now look at how we can train the model that we just defined. The logic of training is contained in the train method inside helpers.py. Let's skip over the first few lines of this method and focus on the creation of the dataset and the data loader. We use data loaders to break the training data into sections and train on one section at a time. We could train on the whole dataset at once each time, but doing that would take more time, and there are some data science benefits that I won't get into. The next line instantiates the machine learning model and puts it into training mode. If the GPU is available, we use it to speed things up. Let's now look at the loss function. This function determines how we penalize errors. The most common loss function used for regression models like ours is the MSE loss, which stands for mean squared error. The loss function squares the difference between predicted and actual values. The problem though is that MSE doesn't work very well when the target distribution has fat tails, which our dataset has. Calling the chart Y histogram method shows you what I mean. The blue bars are the actual distribution of our target data. The black line shows what the distribution would look like if it had what you call the normal distribution. As you can see, the actual data are bunched up more near the middle than the normal. And then if you zoom in to the left tail in particular, you'll see that there are more large negative values than the normal distribution would suggest. If you use MSE loss, getting these tail values wrong would have a much higher impact than getting the values in the middle of the distribution wrong. We don't necessarily want that because then our model would only care about getting the tail values right and not care so much about the middle values. The Huber loss, on the other hand, is more lax on the errors above a threshold, and that's why I've used it. I set the threshold to be 2%. Errors of greater magnitude are still penalized, but not overly so. The next line sets the algorithms for finding the best parameters in the model. I've chosen to use the popular algorithm called ADAM with a typical learning rate. The weight decay value helps mitigate overfitting. You can think of weight decay like medicine. Taking more will attack the disease more aggressively, but too much can kill the patient. If you set the weight decay too high, every predicted value will be very close to zero. For now, I've chosen to use a very small rate. The final block of code uses all the objects we've created to conduct the training, and it iterates through the dataset epochs number of times. You want to choose epochs so that you give the model enough time to train. But you may also want to experiment with smaller epochs or controlling that more intelligently, because slightly underfit model can sometimes perform better. I won't comment on the rest of the code block because it's mostly boilerplate for training any model in PyTorch. Let's now go back to the main file and call the train method. You'll see that the loss value goes down over time. When the method finishes doing its thing, we have our training model. Let's see how well our model performs. The next 4 lines prepares the test data, which in this code is the data on or after 2020. Notice that it uses the predict method, which I didn't go through in this video because it's mostly boilerplate. The last few lines compares the predictions, which I also call forecasts, to the actual. The scatter chart looks like this. The chart will look a little different each time you train, but in every case you should see a blob close to the 0 mark on both axes. If the predictions are accurate, we should see the dots arrange themselves from bottom left to top right, but we don't see that here. The R-squared metric is also slightly negative here, suggesting that the predictions are not accurate at all. And because the predictions aren't accurate, we wouldn't want to use these predictions to trade with real money. Let's now talk about the potential reasons why this model didn't work and whether there's anything we can do to address them. One possibility is that my model is still overfitting. Even though my model isn't that complex, 2 factors make it more prone to overfitting. One factor is that the data is very noisy. Prices seem to move up and down quite randomly. If you look at the series of output data, you wouldn't find some obvious pattern that the model is missing that our human minds could detect. That makes the model grasp at straws to find patterns, but the patterns it thinks it finds tend to be mirages. The other factor is that we're not using a lot of data. There are less than 7,000 training data points, which sounds like it's enough, but isn't all that much considering the data is noisy. We can solve this by training the model on many stocks data as opposed to just SPYs. Now I've actually implemented that before, and using many stocks does help, but I found that the model is still not good enough to use for training. Another possibility for the model failure is that I haven't chosen the right set of hyperparameters. I could have used different numbers of hidden nodes or used more layers or adjusted the weight decay. But I found that none of the configurations I've tried led to better results. Yet another possibility is that I haven't processed the data in such a way that can maximize LSTM's potential. You could, for instance, transform the data into ones and zeros depending on whether stocks went up or down. We'd have to make some minor adjustments to the model to accommodate the data change. And when I implemented this, I found that the model would be right about 53% of the time, which sounds pretty good. The problem with this though is that all the predictions are positive, meaning that the model thinks you should buy and hold at all times. That isn't much of a trading strategy. So a model that looks good isn't necessarily a model you can make money with. Going back to our original model, the last possibility it doesn't work is that LSTMs, at least in the way that I've used it, don't have the right structure to extract insights from the data. Maybe another type of model, such as the gated recurrent unit or convolution neural nets, will be more suitable. Personally, I don't think LSTMs by themselves are enough to create a tradable strategy. I know it keeps some information in memory, and the way of updating memory looks sophisticated, but I don't think it's sophisticated enough. I think LSTMs can perform better when used in conjunction with other models. I may make another video about doing that, and if you'd like to be alerted when that happens, please subscribe to my channel. Let me close with a plug about myself. I'm a financial advisor in Canada. As you can see, I have a very deep technical background, which is unique for an advisor. I use my technical skills to craft my own algorithms for investing money, and I also use my skills to evaluate other funds that use algorithms. By doing this, I can't guarantee, but I believe I can generate better returns for my own clients. If you're in Canada and you're interested in learning more about what I do, please contact me using the link in the description of this video. I hope you enjoyed this video, and if you have, please hit the like button so that other people can discover it too. Thank you for watching, and see you next time.